Good evening and welcome. This is our fourth annual presidential lecture in the Department of Chemistry. I'd like to take this opportunity to thank President Joffre for sponsoring the seminar series. It's a wonderful opportunity for us. No university can be complete unless it has the opportunity to invite eminent scholars to discuss ideas with students, staff, faculty, and the general public. So this is a wonderful opportunity for us. This evening's speaker is Professor Dudley Hirschbach, who is the Frank Baird Jr. Professor of Science in the Department of Chemistry and Chemical Biology at Harvard University. Professor Hirschbach was born on the West Coast, San Jose. He received his BA in math and his BS in chemistry at, please be kind, Stanford. He subsequently received his PhD in chemical physics at Harvard University. That was in 1958. From 1959 to 1963, he was on the faculty at Berkeley. And after that, Harvard pulled him back to the East Coast, where he became a professor and eventually the Baird Professor of Science. Professor Hirschbach has made very, very, very pioneering studies in the field of reaction dynamics, molecular beam collisions, and really revolutionized physical chemistry. But that's not his only achievement. He's been extremely active in education and science education from kindergarten up, as well as in the public's understanding of science. He's extremely decorated. He's won so many awards, it's impossible to list them all. He's a member of the National Academy of Sciences. He's won the Pure Chemistry Prize of the American Chemical Society. He has the Pauling Medal, the Polanyi Medal, the Langmuir Prize, and he has been awarded the Nobel Prize in Chemistry in 1986. Now, you might think that the Nobel Prize is the summit of achievement, but Professor Hirschbach has had the honor of appearing on The Simpsons, next to no less than Jennifer Garner. So clearly he is a man of diverse talents, and we're very, very happy to have him here tonight. The title of his lecture is extremely intriguing. The Impossible Takes a Little Longer, Reflections on Teaching Science as a Liberal Art, and I think every faculty member and TA will resonate with that title somehow or another. Let's please all welcome Professor Hirschbach to our presidential lecture.
Thank you for your very gracious introduction. You reminded me of things I wouldn't have remembered myself, you know. I'm very impressed. But it has been a great pleasure to visit here again. Had a lovely day talking mostly with young assistant professors, and as I described to the chairman, I was so pleased how excited they were about their research. It's very lovely work, and also about teaching. I really will say things that are about research tonight, too, because I've never felt there's any fundamental difference between teaching and research. It's only a question who you're teaching. If you're doing research, you're teaching yourself and your peers in science. And if you're teaching the future of science. So that's the only distinction I see. But really, these are reflections from a long time doing both research and teaching. I start with something, it jumps too far sometimes, something that really made a huge impression on me when I was a graduate student, my first year at Harvard. I.I. Rabi, a very distinguished physicist, gave a talk on science and the humanities. And he said, as you see here, to my mind, the value of science of the humanities lies not in the subject matter alone, or even in greater part. It lies chiefly in the spirit and living tradition in which these disciplines are pursued. The non-scientist cannot listen to the scientists with pleasure and understanding. Sadly, that is pretty much true, as you, from experiences, will probably agree. And then he said, the scientists must learn to teach science in the spirit of wisdom and in the light of the history of human thought and human effort. And here's the line that really grabbed me. Rather than as the geography of a universe uninhabited by mankind. Oh, man. Okay, so that made a big impression. And since I loved history in particular and art and things like that, this especially resonated to me as a fledgling scientist. But I can refer to other scientists' remarks. One I found only more recently, James Clerk Maxwell. Maxwell, the guy of T-shirts fame, those equations. In science, it is when we take some interest in the great discoverers and their lives that it becomes endurable. That's some words. And only when we begin to trace the development of ideas that it becomes fascinating. Okay, that's a pretty strong statement, eh? All right, but now to my topic. Really, I've always liked the definition of education quoted here. Now, actually, like most fine statements, is attributed to a number of people. But I know for sure that J.B. Conant, who had been president of Harvard for 20 years or so, and before that was a distinguished chemist, said this: education is what's left after all you've learned has been forgotten. Obviously, if there's nothing left, you might have been trained, but you certainly weren't educated. And then a liberal education, I feel this is a good definition. It aims above all to instill habit of self-generated questioning and thinking. That's really what we want to achieve. And this habit, it has to be a habit, is essential for science, of course, but too often it's not really fostered in introductory courses, especially in science. So that's the starting point of my reflections tonight. Now, another thing that I've often reflected on is the challenge of the impossible. The saying that I had on the first slide as a traditional one was one my dad often used. The difficult we do immediately. The impossible takes a little longer. And I really did like, as a kid, that second phrase. It has this heroic ring and so on. But it's so true of science. Over all the decades I've had in science, I've seen, as I say here, intrepid, persevering innovators achieve great things that had been regarded as impossible. It really happens all the time in science, and that's something we should never lose sight of. And so what I want to suggest is how it comes about. How come they're so often achieved, and to emphasize the implications I think this has for the way we should think about science education. But first I want to start with this story that really touched off my whole notion of talking about this way, about an impossible educational triumph. And it conveys, as I think, also key aspects of the scientific enterprise and the kinship of the humanities, the science and humanistic arts. This is a story that I find few people know, even though you've all heard about Helen Keller and Annie Sullivan. But I wonder how many of you know the connection with Alexander Graham Bell. Nobody raises their hand. So good. That means it's a new story to you. It's always great to hear a new story. I discovered this in a biography of Bell by Robert Bruce that I discovered while my wife and I were on a biking vacation in Cape Breton, where there's a wonderful museum to Alexander Graham Bell, who had his lab for a long time in an island right off the shore of Great Britain when he did lots of experiments there trying to develop new inventions. Now, as you probably know, Bell patented the telephone, Everyone certainly knows that. But not everybody realizes how dramatic that was and how it came about. It was in 1876. He was 29. Very rapidly, it became incredibly fruitful, remunerative, and he devoted his life for all the years later to pursuit of other inventions. But he regarded his life work as really the education of the deaf. That's what I hadn't known. His mother-in-law and his wife, later married, were deaf. His father and grandfather were teachers of speech. His family had immigrated and settled near Toronto after in Scotland, his native land. Both his older brothers had died of TB, and they were worried about Bell. In his younger years, he was very frail. So that's why they moved. And soon after, he went down to Boston and began teaching the deaf in Boston. In 1872, he founded his own school for the deaf. Not all of his students were completely deaf, and it was in an effort to develop a means of helping his not entirely deaf students distinguish between the sounds of P and B that led to his invention of the telephone. The reason I mention that little detail is it strikes me as a lesson that citizens should recognize. Sometimes the thing that gets a scientist started, some particular little thing, no one can anticipate what's going to grow from it. Just the problem his not entirely deaf students had with telling P and B apart is the reason he wound up inventing the telephone. I mean, that's a striking episode. Now, another aspect, he had a special advantage. As the historians will emphasize, you can read all this, but the technology needed to produce a telephone all existed by 1872. And there were several, as they were called then, electricians pursuing avidly the possibility of what we now call a telephone. Bell was the one who got there first. By first, it meant he turned in his patent application a few hours before another fellow named Eliza Gray. One result was when it soon became evident that this was an extremely valuable patent, he had to defend it in lawsuits for about 20 years after, one after another. He won every single one. And so it's the most thoroughly documented invention in human history as a result of all those lawsuits. One reason he won every one was, first of all the evidence was there. For example, Eliza Gray had written him a letter some months before acknowledging that Bell had in fact solved this problem that Gray hadn't yet solved. That's pretty compelling. But also, all the testimony is that Bell was a wonderful speaker and had great use of language, and it reflected, of course, his lifelong study of language and his father and grandfather's teaching of speech. I could tell you more about that. But Bell was not at all expert. He didn't know, in fact, anything about electricity and magnetism when he set out. And yet only 18 months later, he had invented the telephone. Now, why did he succeed when all these more technically capable people didn't quite make it? Well, in later years, as I put down here, Bell liked to say that the reason he wouldn't have conceived of the principle of the telephone if he'd known more about electricity but less about the mechanics of music and human speech. All right? In fact, he was a good pianist, and it was while playing the piano at the home of his future wife, his fiancée, he had the key idea that you can recognize immediately. The piano soundboard has a lot of kinship with the key thing in the telephone. You want to vibrate something to reproduce the sound. So that's part of the dramatic story. Now, Helen Keller and Annie Sullivan, many of you have seen the movie, I presume. Many of you have read about it. But a lot of people know a few things I want to emphasize. Helen was deaf and blind, but not at birth, but at 19 months after illness. She had a very high fever, and when she recovered from that, deaf and blind. At the age of 6, her parents brought him to Bell because he had a reputation as a teacher of the deaf and all, as well as the inventor of the telephone, to ask if he thought she could be educated. And he was instrumental in arranging to have Annie Sullivan as her teacher. Now, Annie Sullivan had no experience whatsoever as a teacher. In fact, her qualification was she had been temporarily blind for a few months from trachoma. She and her younger brother, Jimmy, were orphans, and they were sent to an orphanage, which in those days was a pretty miserable, only Charles Dickens could have described to you what it was like. But because she had trachoma, she was sent to the Perkins School for the Blind in Boston, which turned out to be a blessing. She, of course, did recover her sight, but that was her one chance to have any really decent education. That didn't happen to orphans in those days. She became the valedictorian of her class, and you can read what she wrote as an 18-year-old. It was tremendous, given a kid who had no education except for a couple years to the master. So she had not much to guide her, as I write here, except her good sense and sensitivity. But only a month after she joined, she was then 20, Helen, came the great moment that you all have heard about, and holding Helen's hand under water from a pump, and managed to convey to Helen what water was, and there's a word that referred to water. Now, within 3 months, Helen was writing brief letters. And within 3 years, she had an astounding command of idiomatic English. I haven't mastered it yet, and maybe some of you haven't either. I mean, it really is very difficult to have a truly idiomatic command. And think what a starting point she had to do that. Now, that was hailed as a miracle. Mark Twain, you might want to look up and read what he says about it. He was absolutely enthralled with this, and many other people were too. Bell, and this is the thing that I found so striking, had a different view. First, you should recognize that in the early years, and really all his life, and for decades, he's helped and supported financially and otherwise both Helen and Annie. And he knew just how they worked with one another. And Bell insisted that Helen's mastery of idiomatic English was, quote, not a case of supernatural acquirement, that's his phrasing, but a question of instruction, a brilliant experiment by Annie. Well, I mean, interested in teaching? What a challenge. Shouldn't we find out what Annie's experiment was? Well, here's what it was. Bell concluded the key was Annie's, quote, constant spelling of natural idiomatic English into Helen's hand without stopping to explain unfamiliar words and grammar. Her encouragement of Helen's reading book after book in Braille with similar reliance in context to explain new language. Because he said this is equivalent to the way a hearing and sighted child learns. The fact is, think back, some of you, how much help did you really give your kids to learn their native language? The fact is they get very little help. Their parents tend to speak to them in baby language, stuff like that, which is not helpful. And what I imagine is these little critters see these big creatures they're living with making sounds, and they react to them. So the little critters say, shucks, I want to try that out. You know, I want to see if I can get a reaction. And little by little, they figure out on their own from context and playing around. And one reason they learn so incredibly well, this very difficult thing of a completely foreign language to them, is they're not afraid of getting it wrong. They just keep playing and eventually get it right. And amazingly, by 3 or 4 years old, every kid speaks with almost completely perfect grammar. Before it's messed up going to school, but we'll come to that later. Okay, so Annie, you can read what she wrote about her teaching, and it's completely consistent with Bell's. she confirmed she purposely never explained anything unless Helen asked a question. And thereby, Annie helped Helen to discover and actively exercise her ability to discern clues and context and learn her own. Okay, I read that, and I said, oh, all these years, I've been trying to explain everything to my students. I mean, if I could only figure out how to do it, I should try Annie's technique. Walk in, all this stuff. And then I reflected, maybe I've been doing that anyway, even when I thought I was explaining things to the students. At any rate, it's something that certainly made me think a lot more about this. So here's a picture I love about Helen and Annie in the garden of Bell's Washington home, 1894, I think it says. Helen was then 14. Annie she would have been 28, and Bell was 42, I think. And you can see Helen's communicating by manual hand signals to Bell, and she's, with her other hand, reading the lips of her teacher, Annie Sullivan. So, I mean, just try to imagine what it's like to be blind and deaf. And before Annie, Helen, who was clearly a very bright young child, was going mad. She's wild, rages, and you've heard about that probably and so on. But then to be able to communicate with people of the caliber of Annie Sullivan and Bell, what a blessing it was for Helen. And you know something about her later career. It's quite amazing. But what I want to emphasize now from this little story is that the teaching style of Annie Sullivan is intrinsic, I think, to research, frontier research in science. Nature, like Annie, is a reticent teacher. She doesn't explain anything. It's up to us to ask questions and generate our own understanding, which of course is always provisional, but it's our own, and it's where we can come from. We can't invoke any supernatural help. We have to realize it's our own, for better or for worse. So really it's true that in frontier research we try to discover or add to knowledge of the vocabulary and grammar of some strange dialect, because as I say, nature speaks to us abundantly, but her languages are all alien. They're not merely foreign, they're alien. But it means that once we decipher some of her vocabulary and grammar in some domain, we can decipher many other messages that she's left for us. So this makes clear or emphasizes how practical curiosity-driven research, which has no other real aim except understanding nature's language in some domain, is in fact incredibly practical and valuable. No matter how much effort I wrote here, you might devote to solve a practical problem, again and again we have the historical evidence that we can't do it until we can read the message. And then in retrospect you say, oh yeah, that was so obvious all along. If we only knew certain things that you had to understand. So ideas and understanding are really the crucial thing. I once got a message, well, it was not in connection with the pinnacle of my career, namely The Simpsons, as you've heard. You got a lot of nice messages about that. But it was on that earlier occasion, and I got quite a few nice messages. Some were in French and German and so on. And even when they're in languages I couldn't really understand too well, human languages, I could decipher because they're pretty simple messages. I got one I couldn't decipher at all. It was in Braille. And of course, that's what I had in mind when I wrote this, that when it comes to deciphering, nature's might as well be in Braille or some other such thing. We have to grope, and we found bumps and things, and it takes a lot of groping and guessing to learn something of nature's language, because we're all born blind and deaf when it comes to it. But as a species, helping each other out and so forth, and playing around like little kids, we have done some remarkable things, and we should be glad of it and of the future prospects of it. Well, implications for science education. Well, in fact, I have the testimony of at least one student who had a course from me, there she is, that I actually have urged students to approach the study of science like that of a foreign language. And I like to say, once you get it in your ear, then it gets easier and easier. But if you don't get it in your ear, forget it. It's going to, especially chemistry, it gets absolutely miserable, unendurable, as Maxwell might say. Because everyone knows you can learn a foreign language if you're eager enough to do so, and you work at it, work at it, work at it. It's very hard at first, and then it gets easier once you begin to learn a little of it and all. Now, actual counts have shown that in introductory science textbooks in chemistry, physics, biology, the vocabulary alone is greater than that in a typical one-year language course, either new words or old words used in new ways. It really is. And then, of course, the concepts and all that meet in the science course function like grammar rules. Every teacher of science who looks at exam questions and so on, you'll find that sometimes the students have gotten a lot of the vocabulary, but they don't have the grammar right, so it doesn't work out. And you're kind of shook up when you see that. So it's like a language, both vocabulary and grammar. Now, so I wrote here, well, here are the benefits of emulating Helen and Annie. It really was an impossible empowerment of Helen by language, and it exemplifies, I think, the highest aim of education, to instill this habit. This habit, I like to emphasize, it has to be a habit of self-generated questioning and thinking, actively scrutinizing evidence, puzzling out answers, trying to attain understanding instead of ritualistic training, cultural perspective, self-reliant thinking instead of conventional knowing. Now, obviously, such approach is equally applicable to science and the humanities. But for both, I think, beginning scientists and students who aren't going to pursue science itself, we ought to emphasize the human adventure of intellectual exploration and help students, above all, take ownership of the subject. The teacher ought to be, in chemical lingo, a catalyst. But it's not a completely appropriate label, because a catalyst, by the conventional classic definition, is supposed to remain unchanged after catalyzing the reaction, in this case, passing on or promoting the understanding and learning of the student. The fact is, as you all know, that teachers actually learn, or should learn, more than the students do when they teach something. So you become an enhanced and empowered catalyst of a term, and maybe there are some molecular catalysts that achieves that too. But whatever we can do to help the students feel that they actually have gained the kind of empowerment Helen did, and that's what you get when you learn a language. Now you have taken ownership of it. That's what we should strive for. Now, I want to talk about what makes impossible possible in science that I find really interesting and that people don't talk about enough, I believe. I say it's because science enjoys a tremendous advantage over other human enterprises. What you're after, call it truth or understanding, waits patiently for you. So there are many ways to illustrate this. I say that's why marvelous advances can be occurred by ordinary human talent, given sustained effort and freedom in the pursuit. In other words, science makes progress not because scientists are smarter than other people, it's because they don't need to be. They have this advantage. In other enterprises like business, politics, sports, sadly last night, sadly, even more, war, the objectives may shift abruptly. A brilliant move may fail because during the time you were implementing, the situation has changed. Every day you read newspapers, such cases. In science, you get to mess up over and over. Miss it. Not recognize what nature is trying to tell us over and over. And we do as a group. And often some maverick or some freak thing sort of allows a breakthrough and you make progress. All that. So I like to say to become a scientist is something like becoming a musician. I don't mean the kind that just turns up a knob high. I mean a real musician like Yo-Yo Ma, for example. Just to pick one at random. But even if you have talent, you have to work hard to master your instrument and the literature and understand the culture of the time to know what the composer hoped you would do in representing or reproducing their music and all. But the scientist can and surely will play many, many, even most of the notes wrong. That's the nature of it. But now and then they get one right and then be appropriately applauded for getting one right. I've always been dazzled by so many productions, performances of musicians, and it might be present with someone else or walking out and just saw what a wonderful performance and say, oh, well, in the second movement, he hit a B flat a little bit off. What? But in science, nobody worries about that. So I like to say, suppose Shaq O'Neal, who gets played millions and is, 7'10" or something or other, he can almost reach the basket and drop the ball in from the free throw line, but he only hits 50% of his free throws. Well, as we were doing it in the scientific way, he had an unlimited chance to shoot. He would always make a free throw because he'd have 50 shots or whatever needed. Likewise, Michael Jordan, who wasn't too good at hitting a fastball in baseball. He'd always get a home run if he had enough chances to swing. So science has this kind of advantage. But we never let on to the students, right? They're conditioned to think science is hard, and only especially smart and talented people can do it, and so on. You see what I mean? It's a fundamental thing that deserves emphasis. But I think it's what makes impossible advances possible, because what we're after is so cooperative, it's so congenial to the human spirit. It's not a chess game, unless your opponent can never make a move. You do much better. Okay, so now I emphasize that the patience of scientific truth is another consequence. Often what might, from what you know at the start, seem the most promising approach doesn't pan out. And then it's very important to have enough freedom and so on so you can have a maverick who's willing to explore unorthodox paths and strain, as I say here, far from the anticipated or consensus route. In fact, in science, it's not even desirable, much less necessary, to be right at each step. I mean, you rarely could possibly be that way. And at the frontier, of course, scientists are heading in the wrong direction much of the time. And they're optimistically looking for new perspectives. I love this quote of Richard Feynman: science is not about what we know, it's about what we don't know. And every advance in science seems to make us more aware of what we don't know. So you could say that our most major product in science is ignorance, appreciation of how much ignorance we have ahead of us. At any rate, it has these ironic consequences for education. Science is met in typical high school or college courses is at odds with this kind of character of frontier research I've been talking about, because too often they come across as a frozen body of dogma to the students. I'm convinced of this. The questions and problems seem to have only one right answer to be found by some correct procedure. I've talked with many students. My wife and I, for 5 years, were co-masters of one of the Harvard undergraduate houses. So I had many opportunities to talk with Harvard students, very bright Harvard students, who had avoided science completely in college. And they all said essentially the same thing, that in their academic trajectory, science or math was the first thing they encountered that seemed to have just this one right answer. And you're supposed to see how to get it by some method that had to be correct and so on, the right way. And if the student doesn't see this right away, they're likely to feel alienated and turn away. And that's what went on. Little scope for personal innovative experience. And of course, it's so far from what real experience and real science is. At the outset, nobody knows the right answer, and often even the right question or approach. So the focus is on asking an interesting question or casting the familiar in a new light. Isn't that sort of a familiar phrase or perspective? Where have you heard that before? Niki, where did you encounter that? When people talk about poetry, right? You know what they say? You cast the familiar in a new light, or see some different perspective. That's really what science, the essence of science is. And if you can achieve that even in introductory courses, you help people get a sense of what real science is like. And with some effort, I think you can make some progress in that direction. That's what I'll talk about for the most time. But before that, I interpolate one question. There's no question that a tremendous burden in science education is this business of exams. They loom so large in students, and especially in this country, we give tests for every little thing, every few weeks or whatever. You don't wait till the end of the year or 2 years or so on later. Einstein hated exams. He had the chance to cut most of his courses as an undergraduate because there was a big exam at 2 years, several parts. And fortunately, he had friends who were conscientious and took beautiful notes, and they lent it to him, and he got through this 2-year exam, and same thing, a 4-year exam at the end. In between, as he said, I could do pretty much what I wanted. And what he wanted to do was read Maxwell, for example, which they didn't teach in his day, even though Maxwell's famous treatise on electromagnetism was published 40 years before Einstein started his undergraduate years in the Swiss Polytechnic and so on. So here's what Einstein's view of exams. It is, in fact, nothing short of a miracle that modern methods of instruction have not yet entirely strangled the holy curiosity of inquiry. For this delicate little plant, aside from stimulation, stands mainly in need of freedom. It is a very grave mistake to think that the enjoyment of seeing and searching can be promoted by means of coercion and a sense of duty. I believe that it would be possible to rob even a healthy beast of prey of its voraciousness with the aid of a whip, to force the beast to devour continuously, even when not hungry. That's Einstein. No, that's just like Maxwell. I mean, pretty strong statement. Is that what you expected? I see someone. No, good. I wasn't searching for the right answer, but you gave the right answer. Anyway, so anyhow, so that interpolate that remark. Whoops, sorry. I poked too fast here. I got to back up. So I think this is the next one. So to come to the poetic thing approach, I say in artistic creations, you don't worry about the right answer. There's no such thing as the right answer in a poem or a painting or anything. But you want a fresh view of something that stirs thoughts or emotions in the observer. And really, that's what scientific work does. The real value of a scientific paper, for example, is in how it impacts the thinking and the doing of the people who study it. Because it's a living thing. If it has no impact, it may be perfectly accurate and admirable even in its craftsmanship, but if it doesn't affect the way people think, they've already felt they understand all that, it's just in the framework of what's known, there's no real value added to the development of the field, then this beautiful paper might as well not have been done. It has no impact. Often a paper that's actually partly wrong has more impact than one that's 100% right in science. because the partly wrong has this very stimulating idea in there. And, of course, other scientists who saw it was partly wrong could leap in and do something about that. If it's completely right, either it kills the field entirely, or, as I just mentioned, it doesn't really add any value, new perspective, or change what they knew before. At any rate, so I say, like art, science is a social enterprise. Its progress depends on the response excited in observers. And it's really the case. So a good way to combat inhibitions induced in students by too much focus on right answers, have them write poems with science themes to enjoy personal freedom and make some topic their own. And some of them have never written a poem, so they're almost as uneasy about doing that, I must confess, as doing the right answer type problems in science. But many of them just write wonderful poems. Here's one of my favorites. I have hundreds of them in files. Carrie Brown, as a freshman, she's an outstanding physician in Pittsburgh now, but she wrote this about quantum land. Do you know a special secret place filling much of invisible space where frogs can only jump so far and the range of an ordinary car can be only 10 or 20 miles, and every person has only half or whole smiles, where dogs bark at specific levels of pitch and people can only be a certain amount rich? I love it. That's a beautiful, it shows she really understands the most important key points in the business of quantization of energy and other properties that underlie all of our understanding of chemistry. And there are many others. Here's another one, another thing. I gave prizes in my class, my freshman class, for the poetry contest. And the book I gave was by Robert Williams Wood. He made woodcuts as a hobby, and he composed these little poems. And you used to be able to get from Dover, I bought as many as 100 copies at a time for $1 a copy, and then the price kept going up. And finally, they quit reproducing it, which seems to me rather weird, because I must have bought 400 or 500 of these eventually. But anyway, How to Tell the Birds from the Flowers and Other Woodcuts, a revised manual of florentology for beginners. Okay? Now, there are about 50 of these little poems that I'll show you one in a sample in a moment. And this book I not only gave as poetry prizes in classes and so on, sometimes even graduate seminar classes where I tried to do this out and had them write poems too, but I would send them to administrators sometimes, pointing out that, as in science, it seemed to me the key points for a good administration were recognizing unappreciated similarities and significant differences, which this is all about, how to tell the birds from the flowers, because in all of his woodcuts, he drew things that look remarkably alike. There's the parrot and the carrot. And then he had the little poem to help you figure the parrot and the carrot one may easily confound. They're very much alike in looks and similar in sound. We recognize the parrot by his clear articulation, for carrots are unable to engage in conversation. Now, try it yourself. Try writing a poem in the format of Robert Williams Wood. Incidentally, he was a distinguished scientist, a molecular spectroscopist in the early decades of the 20th century, and a famous practical joker. He is the guy who was at Johns Hopkins University who persuaded the judge to let him off going through a red light because he explained the Doppler effect. Now he was very lucky that the judge did not understand enough, because to get a Doppler shift big enough to mistake a red light for a green one, he would have to be going pretty near relativistic speeds and therefore be eligible for a really big speeding fine. But anyway, he got away with that one. But there are a number of other remarkable things he did that I won't take time in, but if someone's very eager, I can tell you a few more stories. Now try writing. Here's an example of one by an anonymous poet. Electron in cluster, leprechaun, and custard. These frisky little critters are so mysterious, they've driven many scholars quite delirious. But now their fleeting rights, joys, and most private sighs are spied upon by stroboscopic laser eyes. This is rude, yet met with grace by the merry mites. They dance still faster to confound our throbbing lights. I think that's not too bad. You see, it conveys something beyond just the subject matter, because you can see that throbbing lights, I mean, that really refers to profound limitations of human experience, as well as the subject of lasers teasing leprechauns and electrons and solutions, so on. Anyway, try it out. They're pretty challenging to write. I've tried it myself. But then it's fun to show students some poems that, although they didn't intend to speak about science, speak right about science. One favorite little one here is by a Czech poet, Jan Sekel. Poets don't invent poems. The poem is somewhere behind. It's been there a long, long time. The poet merely discovers it. That's true of science, right? Been there a long, long time. It's waiting patiently. And I don't know about you, but I find it a struggle to write things and find out what I really want to say. And I sometimes feel, I'm struggling, I'm throwing. Finally, I feel a sense of discovery when I finally get, this is what I wanted to say. I don't know why I couldn't just say it. Anyway, I don't know, some of you may have that experience, but I hope not too many as painfully as I usually do. But at any rate, I like it very much. And there are other things you can find like this. Now I'm jumping something again. Sorry. I don't know what's happened here, but this technology is always, this is worse. Slideshow, help! I'll just have to say, okay. I'm willing to accept any help. Important, yes. I had to slip in this. Importance of guessing. It's so important in science. And yet, of course, our teaching method inhibits this. It makes students afraid to guess, and or at least reluctant. Whereas it should be fun. It's natural to want to guess when somebody poses something to you. If we weren't all uptight about it. And you can foster that even in a big class by getting them into little groups, or 3 or 4, and they have to then report as a group and argue about it and so on. Eric Mazur at Harvard does this brilliantly in his physics class. But also guessing is so, you want to try to get students to guess in many ways. In one way I do it, I tell them something I really believe. Not so many years from now, you'll be regarded as an expert in something or other. And then you'll discover that your clients often come to you not because they think you know more than anybody else, but because they think as an expert you can guess better than other people. After all, you don't have to go to anybody to learn some information. You just use your computer and go to the web, right? Of course, there's a little problem to tell the garbage from the good stuff. But still, all information you can imagine is in there some now. It's this guessing, this is judgment thing and so on, that is the key that people are after. And that depends on a lot of experience and so on. My great luck as an undergraduate was to have math courses from Polya. That's why I wound up majoring in math, a wonderful mathematician. And one thing I remember him saying was, the expert makes more mistakes than the novice. Because the expert understands the game so well, they're not so attentive, so they make mistakes. But the difference is, he said, the expert can tell whether this answer makes sense or not. Whereas the beginner may be off 40 orders of magnitude and they have no reference point to realize, whoops, something is right. So that's where this guessing thing is so important. But now, teaching by parables. I want to linger on this a little bit. I developed in this course that you suffered through, or kindly admitted it wasn't so horrifying that it destroyed the rest of your life. I developed a habit with this aim of liberal education to introduce each major subject with what I regard as a parable. And in the student evaluations, they often said, this guy digresses so much. What that meant, I think, was he didn't tell us things that were obviously used on an examination. I really think that's true. You can tell me it was right. At any rate, but I digressed because I planned carefully what I wanted them to get as I thought the most important thing. And so these various parables were that, and they set the stage for the more meat and potatoes stuff, which they had plenty of in Providence on. But one reason was I found even Harvard students were really, many of them, sort of afraid of science. They wouldn't do as well as they might and so forth, and they're worried about medical school, all this stuff. They'd be uptight about it. And I developed this parable business as a way to disarm their fears, but also it allows you to set things in a broader context, open their eyes. It's not just this narrow thing, one technical thing. And there's experimental evidence. After all, if stories are told 2,000 years later, they must have been a valuable educational contribution, or it wouldn't happen. So I really think you should think. For me, a parable is one that has messages beyond the direct message that you can see, in the sense I mentioned about the poem. So I'm listing here quite a few. I'm trying to write a book called Molecular Parables. One that I always started the course you took with is how Aristotle and Galileo were stumped by the water pump. That's the parable that inaugurates discussion of the gas laws. The water pump may sound a long way from the gas laws, but it isn't at all when you talk about it. And related to that is the 13th Labor of Hercules, Sex in the Single Method Group, which I was reluctant to give at Harvard. They're such a stuffy place, students. But out here in plains, Thomas Jefferson's plow is really a very interesting one. Most people, and how nylon won World War II. That's again something that deserves to be more widely known. And I could list more, but I thought I'd just invite the audience. You've patiently sat through this. Is there one on this list you might like to hear? And I can spin out an abbreviated version of it quickly. Is there anybody in favor? I'm interested also to see how many people are for sex and how many are for plows. I mean, out here, maybe you like to hear about plows, right? Here's a volunteer. Which would you like to hear? Wallace Carothers, yes? I didn't know that. Wallace Carothers, as you may have been able to hear him, is buried here in Des Moines. I'd love to hear more about that when we can speak afterwards. All right. I didn't know that. Yeah. Wallace Carothers was a young assistant professor at Harvard when DuPont recruited him to head up what became the polymer division. And very early on, he discovered a version of nylon. It took 13 more years before they developed it into a textile that you could. And of course, it was a sensation. It came out in May of 1941, and you should know what happened in the December 7 of 1941, Pearl Harbor, and of course that touched off the war. But I would, if you want me to tell that parable, I would say that DuPont's undertaking way back in 1923, when people weren't sure there were such things as polymers or just gunk at the bottom of the flask, was a very remarkable thing. And for all these years, led by Carothers, they developed polymer chemistry and, more important even, the polymer chemists and chemical engineers that we wouldn't otherwise have had. Imagine, would any corporation do that today? All these years with no return? And it turned out crucial in the sense that, I might as well finish the parable, a few months after Pearl Harbor, something much more disastrous happened. The Japanese overran the West Indies, where we got all our rubber. You can explain why that was true. And that cut off our supply of rubber. That was a tremendous disaster because rubber turned out, for war fought in that way in those days, the most crucial ingredient for war. You couldn't go to war. It's not just tires, but every moving part needed gaskets and so on. President Roosevelt appointed Bernard Baruch to head a commission, and I have a statement about that. He says the most critical thing, if we don't soon get a supply of rubber, has to be artificial rubber, because the Japanese had cut off the supply of natural rubber. Our domestic economy, as well as the war effort, will collapse. So we undertook a crash program and built 50 plants in the span of less than a year. And within about a year, they were produce enough synthetic rubber so we could start fighting in North Africa. Have you ever wondered why there was a whole year gap before we went to war at all after Pearl Harbor? Whole year. They don't emphasize that in history. They don't mention this either. But if DuPont hadn't started nylon, or what became nylon, we wouldn't have had the chemical engineers and polymer scientists that were the only reason we could build those plants so fast. But there was one other reason we could do it. Our enemies, the Germans, had developed synthetic rubber. All their rubber was synthetic. First thing we did was declare their patents invalid in the United States and then build these plants to make artificial rubber by their method. So the parable has all kinds of lessons. One is just this one, that science belongs to everybody. You can't protect it. You couldn't hide it. So if the Germans hadn't produced synthetic rubber, we couldn't have gone to war at all. Think about that in other contexts. The reason, incidentally, that there was all our supply of rubber came from the West Indies was the British, against all the laws, had violated laws of South America where the rubber tree was indigenous, and for a long time the economies depended on producing rubber. And they swiped, James Bond operation, 70,000 plants, took them and planted them in the Kew Gardens, later in the colonies in Indonesia, and it turned out that killed the whole rubber industry of South America, and they had a nice monopoly, but you know what? It backfired when they guaranteed that nobody could, they had these cannons all pointing out to the ocean. Japanese bicycled through the jungle, and the whole thing fell in one day. See, all kinds of fascinating aspects about this parable. But the real punchline is that it wasn't nylon per se, it was the people that we had to have that made all the difference. So that's that parable, free of charge. But any other parable you want to hear about? We have time for one more, a little shorter. Which one? Jefferson's Plow. Jefferson's whole political philosophy was based on the independent farmer. When he went to France as successor to Franklin, he was appalled, Jefferson was, at the crudeness of French plows. So he set himself the problem to improve them. He recognized it was a calculus problem. The key thing is what's called a moldboard that peels back soil. He realized the shape of this was a maximina problem in calculus. He solved it. He knew calculus. Jefferson had read in original Latin Principia, Newton's Principia. We have correspondence between the physicists of the day, who are many times writing about things that pertain to the Principia, and they knew, Jefferson knew all about it. They sent what we call preprints to them. Jefferson would write back, well, you don't have this quite right. What Newton really just said was this. Think of that. Our third president was pretty good. And stuff like that. Anyway, he solves this plow problem, and the French were so delighted they gave him a gold medal. For 100 years, this was a standard design of the plow. You will see it in statues and so on. The Minuteman statue has a plow and it has this beautiful shape. You all know what I mean for the moldboard. But Jefferson, influenced by Franklin, refused to patent anything. Even though it turned out as our first Secretary of State, it fell to him to implement the patent clause of the Constitution, so he was also our first Commissioner of Patent. There were incidentally 52 of them during the 3 years he served, and he kept them in a shoebox, and that's why in the Patent Office now these great files are called shoes. But it's just free of charge, extra information. But it all contributes to the parable thing of enlarging your picture to see how all these things connect together. So Jefferson, having refused to patent this, he forego huge income and died a pauper. That's why we have the Library of Congress, because Jefferson had to sell his 8,300 books. You know, he was broke. And Congress kindly bought them and started the Library of Congress. Well, we can go on more, but I'm so surprised that you didn't mention some of these other, but another time. So let's wrap up here. Another thing I have to plug is science fairs, because for years I've had the joy of seeing how excited kids are presenting to the public and other kids their projects at science fairs, middle school, high school kids, and so on. It's really a beautiful thing to see. And it's because they take ownership of their project, however humble, however funny, or whatever it might be. It means a lot to them, and it conveys something to their relatives and friends and so on a lot. So I say they enjoy undertaking projects and all that, and done in teams is even more. Now here's an example that I've actually seen. Can you design a bike or tricycle with square wheels so you can pedal at a good speed? Isn't this fun? You ever seen one? Okay, good. And the solution, there is one, exemplifies two basic things about science. First, it opens our eyes to new possibilities. And second, as in biology, the mechanical machines need a suitable environment. So I can see Richard Lasar, who was one of my most brilliant PhD students a few years ago, has already solved it. And here it is. All you do is have a road bed in which the arch matches the side of the square wheel, and then it just goes like, I've ridden this thing. You just you go right along very smoothly and nicely. Of course, turns are a little more sophisticated. However, we could solve a lot of our traffic problems if we use square wheels. I mean, you know, people would have to stay in the right line. Anyway, it's a thing that has the character of a parable. When you think about it, you see more lessons in it. All right, so I'm going to finish now quickly. I wanted to give Robbie a couple more statements I like so much. He in his later life also made statements against what he regards the war against science. I remember he's talking 50 years ago now. So it's a little bit familiar today. I don't have to point out the context. The symptom of both ignorance and a certain anti-rational attitude, which has been the curse of our century. He was speaking, of course, the previous. It is a sort of poison which undermines the self-confidence that leads to the highest development of a rich culture. That's really underscores what's at stake. For example, I don't know the outcome. I don't think it's voted yet, but the Texas Department of Education is going to vote whether intelligent design should be taught instead of evolution. Anyway, and then he urged dedication to build a unified culture in which the sciences describe a world which is alive with people and with feeling, and the humanities describe a world in which the physical universe is not inert matter, but rather a part of the development of the human spirit. I think this is a very nice message. So finally, oh yes, one more. This is a wonderful book, Jacob Bronowski, Science and the Human Values. You may have many of you seen the Ascent of Man series that he was the host for, but very eloquent. He also wrote books about William Blake, who was a Romantic poet and very anti-science because he had a misunderstanding. He didn't understand what romantic science really is. But anyway, but here's Bronowski. Reality is not an exhibit for man's inspection labeled, quote, do not touch. There are no appearances to be photographed, no experiences to be copied, in which we do not take part. Science, like art, is not a copy of nature, but a recreation of her. We remake nature by the act of discovery, in the poem or in the theorem. And the great poem and the deep theorem are new to every reader, and yet are his own experiences because he himself recreates them. They are the marks of unity and variety, and in the instant when the mind seizes this for itself, in art or in science, the heart misses a beat. I get sentimental, excuse me, but I just feel we need to try to convey this sort of thing to students. So finally, I'll finish with something I like a lot, the Nobel benediction, I call it. Everybody's seen these pictures of the Nobel medal, but always the front was Alfred Nobel, which is appropriately enough. But they never look at the back. The back, as I say, it really intends to convey the significance of these things. And the medals, also an inscription that's around the periphery of all of them. In Latin, is this phrase. And in English, you can approximate it as, it's a pleasure to have brought cultivation to life through the discovered arts. Now, of course, in Latin, arts is much broader than just arts and crafts that includes science and technology and art. Anyway, the inscription is used both for sciences and the literature prizes, and I think that emphasizes the cultural kinship of science and the humanities. But let's take a look at the back. That's the reverse face of the Nobel medals for physics or chemistry, and you see there's Scienta. You can't read it too well here, but it's labeled Scienta, of course, science. And she is holding in her left hand a scroll that, of course, represents the knowledge that science has gained. But more important, she's gazing intently at the face of Natura, her teacher, in a classical motif. And Natura has in her right hand this cornucopia of wonderful things waiting for it. So it's a beautiful depiction by Erik Lindberg, a Swedish artist, in 1901. That's been used ever since. And I think I jotted down on the next one, but the thing I want to emphasize here, Scienta reaches up with the right hand, unveil the face of Natura, which she beholds in it. Now, the unveiling motif represents the aim of scientific research, pertains as well to scientific education. For me, this reaches beyond metaphor because these figures morph into teacher and student, Annie Sullivan and Helen Keller. I mean, look at it. Isn't that uncanny? To me, excuse me, I almost start crying. So this is the message I wanted to convey. There's one more thing I had in mind. During talks I gave last year, I always finished with this, and since it's not so deep into this year, it was the centennial of the birth of my PhD advisor, E.B. Wilson, and so I wanted to remind people of that. He was a very outstanding scientist and a marvelous person and a dedicated teacher. He taught a remarkable range of courses, both undergraduate and graduate. He was very interested in a philosophical point of view. He was a fine citizen, rendered service on many national commissions, especially generous in encouraging young people, both students and young faculty. And at Harvard, we have endowed lectureship in his name that goes to young people only. So it was the centennial year of his birth, and happened to be the 50th anniversary of my PhD last year. So I still feel like dedicating particularly this talk to his memory. So thank you. I'd be, of course, happy to respond to questions. it's always nice to have the first question.
The difficulties we have is our students have been beaten with the wrong sticks when we
Yeah.
get them in the university.
Right.
So
It's true. Yeah.
they, in my opinion, the one way they would like to learn, but they would like to learn what they thought science is,
Yeah.
not what science
They've
really
been
is.
conditioned to think those
So what do we
things
do?
already.
Do we wait for
Yeah.
them to open their eyes? We treat all of them like Helen Keller,
Yeah.
and we sort of the first 2 years teach them general liberal arts. I mean, it's really an enigma to even solve this problem for many of us.
Well, it's a
learn.
challenging problem, but the impossible takes a little longer. and you know, I personally feel since, you know, I've tried myself and often seen that students weren't necessarily ready or what I thought responsive to what I was trying to say. I said it anyway because I think, maybe it's foolish to think so, but in time some of it may echo or sink in or whatever when they're more ready. In any case, I really think it's worth making efforts in the direction I've tried to talk about tonight, no matter what, because I just feel that enough people in earshot or whatever will begin to pick it up and little by little contribute to moving the way we do science in the direction that Robbie and so on would, and Maxwell and so on would like to see us do. So I feel, okay, I have the opportunity to try to do this, I should try. And in science we're used to failing, you see, and so we have to have a sort of develop a high threshold for pain and frustration. I mean, I like to tell students that beginning students and veteran researchers are very much alike in one respect, namely, both are confused much of the time. The difference is the researcher is delighted to be confused, because if you're not confused, then of course it must be clear to every other professional, so there's no chance to make a value-added contribution to your field. But because you know that science is so congenial to human spirit, what you're after waits for you, you know, with enough swings of the bat, you'll hit the ball eventually, that you're happy to be confused because you see there's a chance you may learn something really worthwhile that your fellow enthusiasts will say, yeah, that makes me think of maybe I can put this together with that and make another advance. And this is what you witness in your own experience in science, that things you didn't even appreciate of your own work, other people have taken and put it together with things they've done or other people have done. This is what happens in science. It's a very satisfying thing. So anything we can do that tries to convey this aspect, this understanding of science to our students, I think is so important, because they're going to forget all this stuff. Something they didn't want to learn in the first place. And the testing has told them, oh, you're testing, forget. Clear your mind. It was painful. What the hell? But I think they really may understand more of the nature of science if you talk about the kind of things I've tried to discuss tonight. That's what I hope will stick with them when they're citizens, senators, whoever. But I may be foolishly too optimistic. What do you think? I don't really know. But at any rate, I can't help it. I just feel I have to try. I think students really, so many students will surprise you if you can put them in a situation where even if it's a small thing, it becomes their thing. It makes such a difference. Yeah.
So you, I think, gave a very convincing argument for how we look at science in a creative way and try to attract the creativity of poetry, et cetera, into science. But what about the other way? How about if you're off teaching anthropology? Pick a subject, Mike.
Sure, quick subject.
Yeah, quick subject. And so, but that has notions of science, say English or poetry itself.
Right.
How do you start to take science and bring those ideas to that side as well? Because I
Yeah.
also argue.
It's excellent question. Excellent question. I think we have to be more subversive. what we have to do is to startle our friends in the humanities and other fields and so on by being very friendly and having beer with them and stuff like that, and see if, what I mean is subversive, is to seed non-science courses with a little science. Because as long as we continue to have science and math taught in separate courses, then you'll never bridge this gulf that Robbie talked about. Because it would never think of science as part of a more broad culture. But my favorite example there, as I think I mentioned to you before, is a course at Harvard called Tradition and Transformation in East Asian Civilizations, first semester China, second semester Japan. Would you imagine? Not a single mention of science in the whole year. Because, of course, it's science. You can't talk about it, of course, about these civilizations, even though China had such an amazing record of science in ancient times, in Japan in modern times. Oh, no mixing. But I've pointed out to various people, the students call that course rice paddies. And surely many students from this great course have gone home and enthusiastically told their parents about this great course. They had rice paddies. And there must have been some parents who would say, oh, that sounds great. You know, something I always wondered about. Why did those people eat rice? Why not something reasonable like wheat? And the student would say, gee, they didn't mention anything about that. I don't know. And then the parent, in their mind's eye, must see out the window $1,000 bills. and thinking, what the heck kind of education is this? My very sweet, wonderful, alert, eager child is a year at Harvard studying civilizations based on rice, and they never mention why it's rice instead of wheat. And why it is a beautiful story. You may be able to persuade them to put it in, or the analogous thing in other courses. Namely, it must have been discovered empirically millennia ago that rice is the only cereal crop you can grow on the same piece of land 3 or 4 times a year and not add any fertilizer if you flood the paddies. Because then blue-green algae grow. There's a symbiosis between the blue-green algae and the rice plant that fixes from the air just the right amount of nitrogen. If you want to plant wheat on that land, how much fertilizer, nitrogen do you have to add per acre, per year? Surely someone knows here at Iowa State. It's 75 pounds. That's completely out of the question for almost all the world, except ridiculous places like farming practices in certain places I won't mention. At any rate, so that's why it's rice. But that's only the beginning of the story. If it weren't for the blue-green algae, we wouldn't have all these billions of people eating the rice. Because it was blue-green algae that brought photosynthesis, chlorophyll, photosynthesis. It's all chemistry when you get down to it. A few molecules made all the difference. Chlorophyll in particular got it started. And that got oxygen into the atmosphere. When it appeared, it was toxic because the previous life was anaerobic bacteria. But life adapted because it could make a lot of mistakes. We call them mutation. And that made it possible to evolve forms that could use oxygen. That made it possible to evolve larger critters because oxygen metabolism paths are so much more energetic than you have without. And so big creatures ultimately capable of eating rice appeared on the scene. But then you can go on a little bit further because there are a few other key things. To get the really big creatures, you had to have a few other things. One is an energy factory. Cytochromes do that in the mitochondria. And the other is a transport process. Diffusion is very slow. So to diffuse oxygen, speed that sort of commensurate with large creatures that could move and do things, you have to not depend on diffusion through drops. You couldn't make creatures bigger than drops of water. It would turn out, won't work. So you needed something. What is that other something? It's really myoglobin in whales and other critters, and then hemoglobin, which is put together myoglobin that carries the oxygen. With those three things, you got it. Just chlorophyll and cytochromes and hemoglobin, and they're, with a few other spare parts. There you go. So this all connects with rice, why it's rice. So this takes how long? 5 minutes to explain? If you can seed like a virus in these non-science courses, little parables or stories like this that will get propagated using their own reproducing thing in the other course, analogous to how a virus works, that's what I mean by being subversive. If we could do that, if we could seed Jefferson's plow story ought to be part of history class. There are other ones. What about do you know what's at the top of the Washington Monument? There's a little triangle on top. Aluminum. Why?
Precious.
It was the most precious thing then. When that was built, for example, Napoleon III served at dinner parties his ordinary guests in plates of silver or gold, but the place of honor went aluminum plate, because it was very difficult. Aluminum oxide is so tightly held that in order to free aluminum metal was very expensive and difficult. It was more expensive than gold aluminum. How was this changed? It was changed very abruptly by a young man named Hall, who took seriously something one of his teachers said at Oberlin, and borrowed his mother's frying pans, ran electricity into a melt that it was an aluminum ore, and liberated aluminum. As his teacher has said, the liberator of aluminum will make his fortune. Well, it was true. And very soon, the price of aluminum dropped, and it's remained very constant, unlike the price of gold. So we should really have had the world economy on an aluminum standard. It would have been much more sensible than gold and all that. But there are all kinds of sidelights to this picture. I could tell you more, but I will restrain myself once. But that ought to be part of an economics course that makes people aware how quickly something can change just from one discovery. And you have to be able to adapt to that, and on and on. So you can think of a lot of such things that you can think of many more, that if we work at it, we can subversively slip these into non-science courses in a way that they may stay and propagate. I really hope that would happen. But it'd be very small beginnings, but you know how it is. You plant seeds, they do that here a lot, and things grow. So anyhow, sorry I get wound up and I could say more than intended, but are there anyone dare to let me answer another question? So, I don't know. I guess not, perhaps. But thank you very much. Thank you.